Light years, a small phrase that hides a giant truth. You've heard it everywhere, in documentaries, in science news, in movies about space. It feels familiar, almost ordinary. But the moment you try to picture the actual distance behind a light year, your mind slips. Not because you're uneducated, not because the concept is hard, but because the human brain was never built to deal with something this large. The universe forces us to confront scales that break every instinct we have about distance, time, and size. We live our lives inside a tiny bubble of experience. We understand the distance from home to school. We understand the walk to the store, the drive to the next city, the flight across a country. These are distances you can attach memories to. You can imagine the road, the landscape, the time it takes, the effort involved. A kilometre means something to you because you've walked one. 100 kilometres means something because you've travelled it. Even something like 3,000 kilometres still fits into your mental world. It's far, but reachable. You can buy a ticket, board a plane, land somewhere else and say, yes, I've travelled that distance. But the universe doesn't use distances that fit inside human stories. The moment you step beyond Earth, the numbers swell so quickly that it feels like someone changed the rules behind your back. The moon is 384,000 kilometres away. Already this number begins to drift out of your grasp. You've never travelled that far. You've never walked anything close to it. You've never driven a car across anything, even remotely similar. Yet astronauts reached it in 3 days. Rockets tore through the empty space at unbelievable speeds, and still the trip took 72 hours. You can barely imagine that kind of speed, let alone that kind of distance. But the moon is still close. It is the cosmic equivalent of your neighbour's front yard. The sun is 150 million kilometres away. Try to imagine that. You can't. You can repeat the words, you can memorise the number, but you cannot attach the number to any feeling. There is nothing on Earth that prepares your intuition for a distance this large. You can multiply your longest road trip by 1,000 and still not come close. At this point, your brain stops trying to visualise and simply accepts the number as a symbol. You know it's big, you know it's far, but you don't truly understand it. And here's the terrifying part. 150 million kilometres is nothing. It's tiny compared to what comes next. The nearest star after the Sun is Proxima Centauri, and it is over 4 light years away. If you say that in kilometres, the number becomes 40 trillion. A 40 followed by 12 zeros. No one on Earth, not even the smartest mathematician alive, can intuitively understand what 40 trillion anything looks like. You cannot count to 40 trillion in your lifetime. You cannot break it down into familiar units. It's beyond human experience. This is the problem. The universe is too big for human brains. Evolution built us to survive on a planet where knowing the distance to the next river mattered, not the distance to the next star. Our minds are designed to understand meters, maybe kilometers. We were never meant to understand trillions of kilometers. Our senses collapse long before we reach those scales. Our intuition stalls. The numbers become empty. This is exactly why the light year exists. Not because scientists enjoy complicated terms, but because they needed a measurement that turns impossible distances into something meaningful. A kilometre tells you nothing about the universe, but a light year instantly tells you everything you need to know. How long light takes to get from one place to another. Light is the fastest thing in existence. Nothing outruns it. Nothing overtakes it. Even our most advanced spacecraft move at a tiny fraction of its speed. So when a scientist says a star is 4 light years away, it means something specific and powerful. It means the star is so far that the fastest possible messenger in the universe needs 4 years to deliver its light to you. That's a shocking idea. The light from the nearest star isn't from today, it's from years ago. Everything you see in the night sky is old news. The stars you look at are not as they are right now, but as they were in the past. Some changed since then, some might no longer exist. You are always seeing the universe through a delay caused by distance. But before we get lost in stars and galaxies, we need to understand light itself. Light doesn't travel instantly. It has a speed, 300,000 kilometers per second. In 1 second, it can circle Earth 7.5 times. In the time you snap your fingers, light has already traveled hundreds of thousands of kilometers. This speed is not a random number. It is the universe's ultimate limit. According to everything we know about physics, nothing with mass can ever reach or exceed this speed. It's not simply difficult, it's impossible. And yet, even at this unimaginable speed, the universe remains so huge that light struggles to make progress. The sun is 8 minutes away. 8 full minutes. If the sun somehow disappeared right now, switched off like a lamp, you would still see sunlight for over 8 minutes before darkness arrived. Not because your eyes are slow, but because light itself needs that time to reach you. The moon is 1.3 seconds away. Every message sent to astronauts during the Apollo missions took that long to get there, and their responses took that long to return. You can hear that delay in the recordings. The gap between words isn't bad communication, it's physics. Once we start stepping upward, the distances explode. A light hour is over 1 billion kilometers. A light day is over 25 billion kilometers. A light week pushes you into a region of space humanity has never reached and may never reach. A light month places you so far from the solar system that the sun becomes just another star in the sky. And a light year is 9,460,000,000,000 kilometers. A trillion seconds is 31,000 years. Let that settle in. If you counted one number every second without ever stopping to sleep, eat or breathe, you'd spend more time counting to 1 trillion than all of recorded human history. Now multiply that by 9.5. That is 1 light year. You can understand the definition. You can memorize the number, but you cannot grasp the reality. No human can. Our brains don't stretch that far. But the universe does. When astronomers measure distances between stars, they need something that reflects the true scale of the cosmos. Kilometers collapse instantly. 100 million kilometers is already meaningless. 1 trillion kilometers is incomprehensible. After that, you're just adding zeros to a feeling that doesn't exist. But a light year is tied to something real. We know the speed of light, we know nothing goes faster, and we know time always moves forward. So the light year becomes a measurement that fits the universe instead of the human mind. It tells you more than distance. It tells you how far into the past you're looking. Every star in the sky is a time capsule. The closest ones show you their past from a few years ago. Others show you their past from decades ago. Some show you centuries-old light. Some show you light older than entire countries, older than every building you've walked inside, older than every word you've ever spoken. A few show you light older than human civilization itself. When you look at the star Vega, you're seeing it as it was 25 years ago. When you look at Betelgeuse, you're seeing it as it was more than 500 years ago. The light hitting your eyes tonight left that star before telescopes existed, before many languages existed, before entire nations existed. You're seeing the past unfold in the sky every night. This is the power of the light year. It connects distance and time in a way that no other measurement can. It reminds you that space is not only big, but slow, that the universe does not reveal itself instantly. That light needs to fight its way across unimaginable stretches of emptiness to reach you. And this is only the beginning. Our journey outward has barely started. As we move farther from Earth, even light years will begin to feel small. The distances between stars will give way to the distances between clusters. Galaxies will stretch into millions of light years. The edge of the observable universe will stretch into tens of billions. And the scale of everything will grow so enormous that even light, the fastest thing that can exist, becomes painfully slow. But for now, at this starting point, the important realization is simple. Human intuition is not enough. Our minds were built for forests, rivers, mountains, and coastlines. They were not built for stars, galaxies, and cosmic horizons. The universe forces us to rebuild our sense of scale from the ground up, slowly, carefully, step by step, until we reach the point where the size of everything finally becomes clear. This is the moment where the idea of the light year stops being a definition and becomes a doorway. A doorway to understanding distance on the universe's terms, not ours. A doorway to seeing everything differently. The night sky, the stars, the galaxies, and our own place in all of it. By the end of this journey, you won't just know what a light year is. You will feel why it's the distance that breaks our brains. Now that we understand why light is so important, the next step is to walk outward from Earth and see how the universe stretches itself in layers. The best way to understand cosmic distance is to move slowly, step by step, starting from something small enough that your mind can still hold on to it. Instead of jumping straight to light years, we begin with a single second of light. 1 second feels short. You experience thousands of them every day. You never think about them. But when you attach distance to a single second of light, everything begins to change. In 1 second, light travels 300,000 kilometers. That's enough to go from Earth to the moon, almost all the way there, and most of the way back before you finish saying the word 1. The moon feels close when you see it in the sky, but this number reveals just how far it actually is. The astronauts in the Apollo missions didn't glide gently across space. They were launched on a violent, powerful rocket that pushed them faster than any human had ever travelled. And even then it took them 3 days to cover a distance that light could cross in a little over 1 second. When they spoke to mission control, their voices, turned into radio waves, needed 1.3 seconds to reach Earth and 1.3 seconds more to return. That small delay, barely noticeable, was the first taste of how distance becomes time in space. You can almost visualize a light second. It's the first cosmic unit that doesn't completely overwhelm human intuition. But as soon as you multiply it, even by something as familiar as a minute, the numbers start to slip away again. A light minute is 60 light seconds, and suddenly you're talking about 18 million kilometers. This distance is large enough that you could fit dozens of Earths in it and still have room left over. It's also large enough that the delay between planets becomes obvious. Mars, depending on its orbit, can be anywhere from 4 to 22 light minutes away from Earth. That means when scientists send a signal to a rover on Mars, the rover receives it minutes later, not instantly. And when the rover sends data back, Earth receives that data minutes later. This delay turns even the simplest task into a slow, careful dance. You cannot drive a rover in real time. You cannot react to a problem instantly. By the time you see the issue, it's already happened minutes earlier on another world. The sun is over 8 light minutes away from Earth. That alone is one of the most striking facts in the universe. You see the sun shining above you, but you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. If, in some impossible scenario, the sun disappeared at this moment, Earth wouldn't know until 8 minutes and 20 seconds later. The warmth would still feel the same. The sky would still look normal. Nothing would seem wrong. Light would still be travelling toward us long after the event. It's an eerie thought, but it's also a perfect illustration of how distance and time intertwine. Even so, a light minute is nothing compared to what comes next. A light hour is 60 light minutes, over 1 billion kilometers, a distance so large that even comparing it to Earth's size becomes meaningless. If you were travelling in the fastest spacecraft ever built, the Parker Solar Probe, which reaches speeds of almost 200 kilometers per second when it swings close to the sun, this distance would still take you days. Light covers it in 1 hour. 1 hour of uninterrupted motion at the maximum speed allowed by the universe. Saturn is a little over 1 light hour away at its closest. When the Cassini spacecraft explored Saturn, scientists often had to wait more than an hour for a single photograph to arrive on Earth. Imagine trying to take a picture on your phone and waiting an hour to see it. That was normal for Cassini. Engineers had to plan everything in advance because real-time control was impossible. If the spacecraft encountered a problem, the earliest Earth could know about it was over an hour later, and any command they sent back to fix the issue would take another hour to arrive. Space makes even simple tasks feel slow and distant. A light day is 24 light hours, around 26 billion kilometers. This distance is so enormous that nothing human-made has ever reached it. Voyager 1, launched in 1977, has been traveling for nearly 5 decades and is still less than 2 light days away from Earth. It has moved beyond the planets, beyond the influence of the solar wind, into interstellar space, and yet on the scale of light, it has barely begun to move. The spacecraft's speed is incredible by human standards, but compared to light, it is barely crawling. Every message sent to Voyager takes almost a full day to arrive, and every response takes another day to return. A 2-day conversation, with each side waiting patiently for the other to answer. This is what distance means in space. At a light week, the solar system shrinks behind you. If you could somehow travel to a point 7 light days away from the sun and look back with a powerful telescope, you would see the solar system as a tiny collection of faint dots clustered around a bright point of light. The giant planets like Jupiter and Saturn would be small and dim. The inner planets, Earth, Mars, Venus, would be almost invisible. You would be so far away that the sun would no longer dominate the sky. It would look like a star. A large one, but a star nonetheless. A light month pushes you even deeper into the emptiness. At this distance, the sun is no longer overwhelming. It is simply one of many stars in the blackness, bright but no longer special. The planets are impossible to see. The solar system is reduced to a tiny glowing dot surrounded by darkness. You would feel completely alone, floating among countless stars, each separated by enormous distances. And finally we reach the light year, the unit that forces the human mind to surrender. You've walked through the smaller steps, and every one of them has stretched your imagination farther than it was meant to go. Now multiply all of that by 12 months, 52 weeks, 365 days, 8,760 hours, 525,000 minutes, over 31 million seconds. And you finally reach 1 light year, 9,460,000,000,000 kilometers. Say it slowly. It still won't feel real. You can break it into smaller pieces. You can convert it into numbers you recognize, but nothing will make it feel familiar. It is the scale where language stops being helpful. The human mind can imagine thousands. It can stretch to millions. It can grasp billions with effort. But trillions lie beyond the edge of intuition. A trillion is 1,000 billions. A billion is 1,000 millions. The distance between these words is enormous, yet the brain treats them as if they live in the same neighborhood. They do not. 1,000,000 seconds is about 11.5 days. 1,000,000,000 seconds is 31 years. 1,000,000,000,000 seconds is 31,000 years. Multiply that by more than 9, and that is 1 light year. So when astronomers say the nearest star is 4.24 light years away, they are telling you something extraordinary. They are saying that light, moving at the fastest speed possible, needs over 4 years to reach it. They are saying the universe is structured in distances that bend the mind. They are saying that even when you use a measurement as enormous as a light year, the universe still needs dozens, hundreds, thousands, millions of them to describe itself. Everything we've talked about so far, light seconds, light minutes, light hours, light days, light weeks, light months, all of that fits inside a tiny bubble around the sun. It barely touches the space between stars. The cosmic yardstick grows so quickly that even minutes and hours turn into nothing. You can cross the entire solar system in fewer than a dozen light hours from end to end. But to reach another star, you need years. Light years. That is why the light year matters. It's not just a number. It's the first step into true cosmic distance. It's the point where you realize that everything you've ever known, Everything you've ever seen, every story, and every life that has ever existed takes place inside a tiny pocket of space that light crosses in a handful of hours. Beyond that tiny pocket is the darkness, stretching for years before you meet the next star. Once you understand that, you understand why the universe challenges our imagination. You understand why astronomers needed a new kind of measurement. And you begin to see that the distances between stars are not just far, they are so vast that they redefine what distance even means. We have now reached the edge of the familiar. The next steps will take us out of the solar system completely into distances measured only in light years. And once we do that, everything will change again. As we move beyond minutes, hours, and days of light, the universe begins to reveal how truly slow our machines are compared to the speed of light. We've always been proud of our technology. We celebrate rockets, spacecraft, engines that roar and push metal shells into the sky. But when you measure distance the way the universe measures distance, the truth becomes painfully clear. Everything we have ever built crawls. The numbers that once felt spectacular begin to feel small. The speeds that once felt unbelievable become almost motionless. And the gap between human capability and cosmic scale becomes overwhelming. It starts gently. Think about Voyager 1, the farthest human-made object from Earth. Launched in 1977, carrying messages from humanity on a golden record, it has been travelling for nearly half a century. It has crossed the orbits of the outer planets, passed through the edge of the solar system, and entered interstellar space. It has travelled so far that sunlight reaching it is more than 700 times weaker than sunlight on Earth. Yet for all that distance, Voyager 1 is still less than 2 light days away from us. 2 days, after almost 50 years of non-stop travel at tens of thousands of kilometres per hour, it has not even finished the first week of light. This is where the scale begins to hit you. We have spent enormous resources building rockets powerful enough to fling spacecraft across the solar system. We can land machines on Mars, fly drones on alien worlds, orbit giant planets, and send probes into the deep. But even our best work barely registers on the cosmic scale. Light covers in hours what takes us decades. Light travels in days what no human mission will reach for centuries. A light hour stretches over 1 billion kilometres. Even planets feel small compared to this distance. If you stood at a point 1 light hour from the sun and looked back, the sun would still be the brightest object in the sky, but it would no longer feel close. You would be outside the orbit of Saturn, floating in a vast and silent region of space where the sun is simply a glowing disk in an endless black sea. Everything familiar would be behind you, shrinking into a tiny cluster of planets around a distant star. Now imagine you lose track of time, and an entire day passes. Light continues racing forward at its unstoppable speed, covering 26 billion kilometres in that single day. If you could somehow travel alongside it, hour after hour, the solar system would shrink behind you with incredible speed. The planets would quickly compress into small dots. The sun would dominate the sky less and less. Eventually, you would reach the region where Voyager 1 drifts, silent and alone, carrying humanity's voice farther than anything we have ever launched. Seen from the perspective of light, even Voyager seems like a slow, drifting leaf in a cosmic ocean. This is the first moment where you realize that we are trapped by our own speed, not because we lack imagination, but because physics sets hard limits. Light speed is the fastest anything can go. Everything else falls behind. The universe ignores our pride in rockets, because rockets cannot cheat the laws of motion, energy, and time. As the distances grow, something else happens that is even harder to accept. Our ability to stay connected with our machines fades. When a spacecraft orbits Mars, the signals take minutes to reach us. When Cassini orbited Saturn, the delay stretched to over an hour. When Voyager sends a message from interstellar space, the delay becomes nearly a full day. This means that the farther we explore, the more outdated every piece of information is by the time we receive it. We never see our spacecraft as they are. We see them as they were hours ago. We watch their past. They operate without us in real time, making decisions on their own when needed. If we ever reach a distance of one light week, communication becomes surreal. Imagine sending a message to a spacecraft and waiting 7 days to learn whether it even received the signal. Then waiting another 7 days to get the reply. 2 weeks for a single exchange. It becomes impossible to guide anything from Earth at such distances. Missions would need to be completely independent. A spacecraft that far away would operate like a robot civilization in miniature, taking care of itself, solving its own problems, updating itself without any human intervention. The only role Earth would have is listening to its ancient signals arriving from the past. A light month is 30 days of light-speed travel. At that distance, the sun becomes just another bright star in the sky. You would no longer see the solar system as a structured set of worlds. The planets would be invisible. Even Jupiter, the largest planet we have, would disappear into the brightness. The sun would shine, but it would not dominate. There is something strangely emotional about this idea. The solar system, which feels enormous to us, becomes tiny when you step back just one light month. Humans are used to thinking of the solar system as vast. We imagine the journeys of probes that took years to reach Jupiter or Saturn. We picture long arcs of spacecraft looping around planets using gravity assists. We admire the engineering behind every interplanetary mission. But at one light month from the sun, all of this collapses into something minuscule. Our entire cosmic neighborhood shrinks into a point of light, surrounded by nothing. This is where the mind begins to let go of old ideas. You start to understand why distances beyond the solar system are measured in light years. It's not a choice, it's a necessity. Kilometers fail. Astronomical units fail. Everything familiar fails. The universe stretches so far beyond human travel that the only unit matching its scale is the distance light travels in a year. To reach the nearest star system, you would need more than 4 light years. That is more than 4 times the distance light covers in an entire year of constant motion. Now think about that. We celebrate Voyager for reaching 2 light days, and rightly so. But the gap between 2 light days and 4 light years is as wide as the gap between a mountain and a galaxy. Voyager's achievement is spectacular, but it's also a reminder of how far we still have to go. The fastest spacecraft humans have ever built would take tens of thousands of years to reach Proxima Centauri. Generations would be born, live and die before the spacecraft reached its destination. Civilization would change, languages would evolve, entire eras of human history would pass, and the spacecraft would still be drifting through darkness, inching toward a star so far away that light itself needs over 4 years to reach it. Now consider something even more extreme. Imagine launching a spacecraft capable of reaching 20% the speed of light, a concept being explored in theoretical projects like Breakthrough Starshot. Even travelling at that staggering speed, the spacecraft would still take more than 20 years to reach the nearest star. 20 years of racing through interstellar space at a speed thousands of times faster than any rocket we have today. And even then, after 2 decades of flight, the spacecraft would have only crossed the distance we call nearby. This is the cosmic reality. The universe is large beyond imagination, and light is the only traveller that moves fast enough to make the distances comprehensible. Everything else moves in slow motion. Everything else turns into decades, centuries, or millennia of travel. And yet there is something beautiful in this, something unexpectedly profound. The slowness of our machines forces us to see the universe the way it is, not the way we wish it were. When you realize how far away everything is, you understand why the night sky feels so quiet. Stars are separated by oceans of emptiness. Galaxies are separated by gulfs so huge that even light struggles to cross them. Everything in the universe is held together by gravity, but everything is also kept apart by distance. Once you pass the boundary, where hours and days of light become meaningless, you begin to see the truth behind cosmic silence and cosmic patience. The universe operates on scales far beyond human lifetimes. It plays out slowly, quietly, steadily. Stars burn for billions of years. Galaxies drift for aeons. Light moves message by message across distances so vast that our species might rise and fall before some of those messages ever arrive. And still, light never stops. It flows endlessly through space, carrying information from every corner of the cosmos. It is the only thing fast enough to give us a chance to understand where we live. Every star you see is sending light that began its journey long before you were born. Every galaxy you observe through a telescope is showing you what it looks like before humanity existed. Light's journey is the universe's way of telling us its story, slowly, carefully, with delays measured not in seconds, but in years, centuries, and millions of years. Part 4 marks the place where human intuition finally loses its grip. Hours and days no longer help. The solar system becomes a dot. Everything we've explored, everything we've touched, everything we've built sits inside a tiny bubble that light crosses casually. The universe opens itself in larger and larger steps from here, and each step will reveal something stranger, older, and farther than anything before. We are now standing at the edge of the familiar. The next step is the true leap, the light year itself, and the beginning of distances so enormous that human imagination breaks completely. As we move past the outer edges of the solar system, we start entering a place that doesn't feel like anything we know. The planets fade away, the sunlight weakens, and the familiar structure of our home system dissolves into a region that feels empty, stretched, and silent. This is where the idea of distance begins to change in a deeper way. Up until now, we've talked about seconds, minutes, hours, days, weeks, and even months of light. Those were already far beyond anything humans could travel, but they were still linked to the solar system. They were still inside a neighborhood with a center, a star, and planets orbiting it. But once we move beyond a few light months from the sun, we begin leaving the solar system entirely. Not just physically, but conceptually. The solar system is not simply the region where planets orbit. It extends much farther than the planets themselves. Long after you pass Neptune, long after you pass Pluto, long after the planets have vanished behind you, you are still technically inside the solar system. The sun continues to influence the space around it in subtle ways. Its gravitational pull stretches far into the darkness. Its particles flow outward in a stream called the solar wind. This wind creates a bubble around the solar system known as the heliosphere. Inside it, the sun's charged particles dominate. Outside it, the environment belongs to interstellar space. Voyager 1 crossed the boundary of the heliosphere in 2012, 35 years after it was launched. By that time, it had travelled almost 20 billion kilometres. It had moved through space for longer than many of the scientists who built it had been alive. It had seen the giant planets up close. It had sent back thousands of images and measurements. And still it was only at the edge. Only then did it enter interstellar space, a place where the particles floating around it no longer belonged to our sun. Voyager's crossing wasn't dramatic. There was no visible line, no signpost, no sudden shift. But the delta changed. The density of particles shifted. The behaviour of magnetic fields changed. And scientists knew that humanity had finally launched something beyond the influence of the star that gave us life. Yet even at that boundary, even after 35 years of travel, Voyager was nowhere near the next star. In terms of light travel, the entire journey only amounted to a fraction of a light day. A tiny slice, a step so small that if light could speak, it wouldn't even acknowledge it. This is the moment where the true scale of the universe begins to reveal itself. Interstellar space is not a place you arrive at quickly. It is not a region you cross in a day or a week. It is a gulf so wide that even the fastest phenomenon we know, light, takes years to cross it. Imagine you are floating 3 light weeks away from the sun. You look back, and the solar system is just a bright dot. The planets are invisible. Even Jupiter, which once looked huge and majestic, would be swallowed by distance. The sun remains bright, but it no longer dominates your view. It's simply one star among many. Around you is darkness that stretches in every direction, deeper than anything you've seen so far. If you look forward, toward the next star, you will not see it. It is too far, too faint, and its light too spread out. What lies ahead of you is emptiness so complete that it becomes difficult to understand that stars even exist. Move another few light weeks. Now you are a full light month away from the sun. At this distance, you have broken your connection to the solar system entirely. The sun remains visible, but it doesn't look like home anymore. It looks like a bright star, a familiar colour, but nothing more. You could point to it and say, "That's where I came from," but that thought would feel surreal. There are thousands of stars in the sky around you. Many of them look similar to the sun. Without precise instruments, you might not even recognise which one is yours. This is the deepest kind of isolation imaginable. You're not just separated by kilometres or days, you're separated by light. This distance isn't measured by how far you can travel in a ship. It's measured by how far light can travel in a month. And kinse, the fastest thing in existence. At this point, the word far loses all meaning. This is not distance the way humans experience distance. This is distance that belongs only to the universe. And yet, even here, even at 1 light month, you are not close to another star. The space between stars is vast, cold, and empty. It stretches for years. Light months are tiny building blocks. To reach the nearest star, you would need over 50 light months stacked end to end. Imagine travelling 1 light month, then doing it again, then again, 50 times. Only then do you arrive at the first other star system, Alpha Centauri. Before we look at the stars themselves, we need to understand the emptiness between them. Movies often show space as a place filled with glowing dust, swirling colours, and dramatic visuals, but real interstellar space is almost perfect nothingness. On average, in every cubic centimetre, a volume the size of a sugar cube, there might be one atom. One. On Earth, the air around you contains billions of atoms in that same volume. The emptiness between stars is so extreme that it feels almost artificial. Yet space is not completely empty. Invisible fields stretch across it. Radiation drifts through it. Dust particles float silently for millions of years. Stray comets wander slowly along their orbits. But the most unsettling thing about interstellar space is its scale. You can travel for months at the speed of light and still be nowhere. You can travel for years and still have stars far away in every direction. You can travel for centuries with a normal spacecraft and barely move out of your starting position. Leaving the solar system feels like trying to swim across an ocean that has no shore, no islands, no currents guiding you, and no way to measure your progress except by watching the faint glow of home shrink behind you. After a while, even that vanishes. If you could float 5 light months from the sunlight reaching you would be so weak that it wouldn't feel like sunlight anymore. It would just be part of the general glow of the galaxy. By 10 light months, the sun becomes less bright than many stars you can see around you. Earth and the planets would be so small that no telescope could ever find them. The entire solar system would disappear into the background. At 1 light year away, you wouldn't just be outside the solar system. You would be so far away that the sun could easily be mistaken for an ordinary star in the night sky. If you didn't already know where to look, you would never find it. It would look like a slightly bright point of light, nothing more. This is the moment when you understand why stars form a galaxy and why galaxies seem so dense when viewed from Earth. The sky looks full of stars not because stars are close together, but because your eyes gather light from enormous distances. A galaxy is filled with stars, but each star is separated by light years of space. If you stood halfway between two stars, you would see nothing but darkness in every direction. Stars only look bright because you're always far enough away that their light can spread evenly and still reach you. Now imagine that you're travelling outward at a constant speed and the sun grows fainter behind you. Every month you move, it dims. Every month you move, it shrinks. Every month you drift, it becomes more like all the other stars around you. You're moving through interstellar space, a region so enormous that your entire lifetime is not enough to cross it. You begin to understand that the gap between stars is not something humanity can bridge easily. It's not a road you can pave, not a highway you can build, not a challenge you can overcome with simple engineering. It is a fundamental barrier set by the universe itself. But even in this emptiness, something subtle and beautiful exists. As you drift farther from the sun, you begin to see the larger structure of the galaxy. The Milky Way band becomes brighter and more detailed. Dust lanes stretch across the sky. Clusters of stars appear in patterns you've never seen from Earth. Without the glare of the sun, the galaxy reveals itself in full. You see billions of faint stars that were once too dim to notice. You see the glow of distant clusters. You see the spiral arms stretching across the darkness. Like a vast river of light, it becomes clear that interstellar space, while empty, is not lifeless. It's a highway of photons moving endlessly from one place to another, carrying the history of the cosmos. This is where we stand after leaving the solar system, in a space where human intuition finally fails for good. A place where distances are measured in months and years of light travel. A place where the sun becomes insignificant. A place where everything familiar feels impossibly far away. And yet, this is only the beginning of interstellar distance. 1 light year is barely the first step toward another star. The space between stars is so large that even light, fast as it is, takes years to cross it. We have now reached the edge where our home ends and the true galaxy begins. We've left the solar system behind, stepped into interstellar space, and begun to see the universe on its own terms. From here, the next part of our journey will take us to the nearest stars themselves and reveal why even the closest ones are impossibly far out of reach. A light year is one of those ideas that sounds simple when you first hear it, but the moment you try to imagine it, it slips out of your hands. You understand the words, you understand the definition, but the reality behind the definition is so enormous that your brain refuses to form a picture. A light year is the distance light travels in a vacuum in 1 year. You can repeat that sentence, you can memorize it, but the truth is much bigger than the words. To see it clearly, you need to step inside the meaning. Light travels at 300,000 kilometers every second. That number alone is already impossible to picture. Try counting seconds in your head. 1, 2, 3. In each of those seconds, light has traveled farther than any human has ever gone. Now let that speed continue for 10 seconds, for a minute, for an hour, for a day, for a week, for a month. If you try to visualize it, your mind gives up somewhere along the way. The numbers go off the chart. After 1 year of non-stop travel, light has moved 9,460,000,000,000 kilometers. Most people have never even dealt with the idea of a trillion, and here the universe casually multiplies it by 9 and more. If you try to write this number out and place it next to things you understand, it doesn't help. It's too big for comparison. If you tried to walk it, you wouldn't get anywhere. If you tried to drive it, you wouldn't even scratch the surface. If you tried to fly it in a jet, you wouldn't make noticeable progress in thousands of lifetimes. If you use the fastest spacecraft humans have ever created, the distance still remains unreachable on any human timescale. What makes a light year so overwhelming is not just the size of the number, but the meaning behind it. A light year is not like a kilometer or a mile. It is not a number tied to human experience. It is tied to the speed of the universe. It is tied to time itself. When you say something is 1 light year away, you are saying it is so far that even the fastest possible traveller, the fastest messenger in existence, requires 1 full year to reach it. That is not just a distance, that is a time delay carved into the shape of the universe. Imagine standing in complete darkness, looking at a single star. The light entering your eyes left that star a year ago. Whatever that star looks like right now, you will not see until next year. If the star changed, if something dramatic happened to it, if it dimmed, if it brightened, if it exploded, you would remain unaware for 12 full months. The universe is always showing you the past, and the light year is the scale by which that past reaches you. Now try to imagine the actual size of a single light year in physical terms. If Earth were a tiny dot on a sheet of paper, and you place the moon less than an inch away, and the sun several feet away, and the outer planets scattered across the room, the nearest star would not be in your house anymore. It wouldn't be in your neighbourhood. You would need to walk down the street, cross several blocks, and maybe even go to another town before you reached a spot where you could draw Proxima Centauri. That's the scale we live in. Our solar system is a small speck inside a vast emptiness where even nearby stars lie years apart. A single light year contains so much emptiness that it almost feels unreasonable. When you picture space, you might imagine stars sitting close together, planets circling them, galaxies glowing in bright clusters. But that's not the real structure. The real universe is spacious, stretched, almost unbelievably empty. Stars are not next door to each other. They are separated by oceans of darkness that take light years to cross. Our star, the sun, shines brilliantly in our sky, but from 1 light year away, it would be nothing more than a tiny spark. If you floated in that darkness, you would not see any planets. You would not see Earth. You would see a faint point of light, one among countless others. This is why astronomers use light years, because kilometers do not stretch far enough. Even millions of kilometers stop being useful once you leave the solar system. A number like 40 trillion kilometers, the distance to the nearest star, has no meaning in everyday life. It is too big, too abstract, too isolated from human experience. But when you say 4 light years, something changes. You understand immediately that you're talking about a distance measured in years of travel at the speed of light. You understand you're talking about a distance that nothing slower than light can cross quickly. Even the idea of walking a light year becomes absurd when you think about it. If you decided to take a step every second for the rest of your life, and if you lived for 90 years, you would only complete around 3 billion steps. You would need 3,000 lifetimes just to reach 1 trillion steps. And after all those lives, after thousands of years of endless walking, you would still be far from covering the distance of a single light year. That doesn't just show how far a light year is, it shows how small our lives are compared to cosmic scales. And yet, a single light year is tiny compared to the distances we will face later. There are stars hundreds of light years away, thousands, tens of thousands. There are structures in the galaxy so large that they stretch across hundreds of thousands of light years. There are galaxies millions of light years apart. There are clusters and superclusters where distances are measured in tens or hundreds of millions of light years. And beyond that, the observable universe extends to nearly 46 billion light years in every direction. Everything we explore later rests on the idea of the light year. You cannot navigate the universe without it. You cannot talk about stars, galaxies, or cosmic history without it. You cannot understand how big the universe is unless you first understand how far light travels in 1 year. A light year is also a reminder that time is always involved when you look into space. If you observe a star 50 light years away, you're seeing it as it was 50 years ago. 100 light years away means 100 years ago. 500 light years away means 5 centuries in the past. This creates a strange experience. The farther you look, the deeper into history you go. The universe is not showing you a single moment. It is showing you layers of time unfolding at different Speeds. This idea becomes more dramatic when you apply it to larger distances. A star, 1,000 light years away, shows you the world as it was around the time when ancient civilizations were forming. A star, 10,000 light years away, shows you the world long before humans walked the Earth. A galaxy, a few million light years away, shows you a universe before humanity existed in any form. The light year connects our understanding of distance with our understanding of history. Sometimes the light you see is older than everything you know. When scientists say something is 1 light year away, they are not simply giving you a measurement. They are telling you how long that light has been traveling. They are telling you how far into the past you're looking. They are telling you that space and time cannot be separated. 1 light year is 1 year of history, 1 year of motion, 1 year of cosmic storytelling. And there is something humbling about that. You realize how brief the human experience is compared to the universe. You realize how tiny Earth is, how small our lives are, how short our history is. But you also realize how extraordinary it is that we can even measure such distances. How amazing it is that our species, existing for a flash of time, can calculate the journeys of photons that began long before we were born. The light year also reminds us why faster than light travel, as exciting as it appears in fiction, is nearly impossible according to our current understanding of physics. Nothing with mass can reach the speed of light. To accelerate to that speed, you would need infinite energy. This limitation means that crossing light years is not just a matter of building better engines. It is a matter of working within the laws of the universe. The great emptiness between stars is not something we can ignore or shortcut. It's a fundamental feature of reality. Yet despite all these limitations, the idea of the light year inspires hope. It tells us that even though the universe is enormous, we can still explore it, not by traveling there physically, but by studying the light that reaches us. Every telescope, every detector, every instrument we use allows us to collect photons that have traveled for years, centuries, or millions of years. When you look at a star through a telescope, you are capturing a piece of its history. When you study a galaxy, you are studying a chapter of its story written in light. A light year is distance. But it is also narrative. It is a record of everything that light has witnessed on its long journey. And because light travels at a constant speed, every photon carries a timestamp embedded in the universe's rules. When you think of it this way, a light year becomes more than a scientific concept. It becomes a bridge between us and the cosmos, a way to connect our short lives with the vastness of space. It becomes the only unit that makes sense when the universe grows larger than imagination. By understanding 1 light year, you unlock the scale of everything else. You understand how far stars really are. You understand why galaxies seem faint and distant. You understand why the night sky is a map of ancient events. You understand why cosmic distances break the brain, and why the universe is far stranger and larger than anything we experience on Earth. 1 light year is only the beginning. From here, the distances stretch into thousands, millions, and billions. But the foundation remains the same. Everything in the universe is measured by how far light can travel in time. We have now reached the moment where the idea of a light year becomes real, not just a definition. The next step is to meet the stars themselves, the first neighbours of the sun, and to understand why even the closest ones are so hard to reach. When you finally grasp what a light year means, the next question becomes unavoidable. If a light year is so large, how far away are the nearest stars? And this is where reality becomes even stranger. We tend to imagine the universe as a densely packed place with stars sprinkled everywhere, like glowing dust. In movies and illustrations, starfields are crowded, bright, almost overflowing. But that image is a lie. The universe is mostly empty. Stars are incredibly far apart. The space between them is enormous, lonely, and almost painfully vast. Our closest stellar neighbour is Proxima Centauri. It is part of a triple star system called Alpha Centauri, which includes two sun-like stars and the smaller red dwarf we call Proxima. This star is the closest thing to us beyond the Sun, the nearest step on the cosmic ladder. And how far away is it? Over 4 light-years. To be exact, about 4.24 light-years. That number might feel familiar now, but the reality behind it is staggering. Light, travelling at the maximum speed the universe allows, needs more than 4 years to reach that star. If the Sun disappeared right now, we'd find out in 8 minutes. But if Proxima Centauri vanished at this moment, we wouldn't know until the middle of the decade after next. That is how far it is. That is how long light requires to cross that gulf. This distance is not just inconvenient, it creates a barrier that is almost absolute. With our fastest spacecraft, it would take tens of thousands of years to reach the nearest star. Even the fastest probes humanity has ever imagined, the ones proposed for the future, would still take decades at speeds that are extremely difficult to achieve. The nearest stars are close only in a poetic sense. In physical reality, they are impossibly far. If you stood somewhere in interstellar space, halfway between the Sun and Proxima Centauri, you would be surrounded by darkness so deep that neither star would feel dominant. The Sun would look like a bright point in one direction. Proxima would look like a dimmer point in the opposite direction. Everything else would be scattered stars, faint and far away. It would be the loneliest place imaginable, a midpoint in a journey that light itself takes more than 2 years to cross. Proxima Centauri is a small, cool red dwarf. It is not a grand, bright sun like ours. It's dim, low in temperature, and invisible to the naked eye from Earth. Yet despite its quiet appearance, it has planets. One of those planets, Proxima b, lies within the star's habitable zone, where temperatures might allow liquid water. This discovery shook astronomy when it was announced. The nearest star has a potentially Earth-like planet, but the distance makes exploration almost hopeless for now. The star is sitting right beside us in galactic terms, but on human terms, it might as well be in another universe. When scientists talk about sending probes to Proxima Centauri, they're not talking about rockets or crewed starships. They're talking about microscopic spacecraft, wafer thin, pushed by powerful lasers to reach 20% of the speed of light. At that speed, a journey to the nearest star would still take more than 20 years. Those 20 years would be filled with challenges, collisions with dust grains travelling at extreme speed, communication delays, power limitations, and the harsh environment of deep space. Even imagining such a mission requires abandoning everything we know about traditional spacecraft. And that's just the nearest star. When you expand your view beyond Proxima Centauri, the numbers grow quickly. There are dozens of stars within 10 light-years of Earth. Most are red dwarfs, dim and faint. A few are similar to the Sun, but even the closest among them are several light-years away. Visiting any of them requires travel across vast stretches of empty space. They are not neighbours in the way cities or countries are neighbours. They are separated by distances that freeze your imagination. Picture the map of the solar system. Now imagine zooming out until the planets become dots. Zoom out farther until the Sun becomes just another star. Then zoom out even farther. At this scale, the stars near us form a loose cluster, not touching, not crowded, each one a lonely island. If you lived on a planet orbiting another star and looked out at the universe, the Sun would appear as nothing more than a faint point of light. You would not know it was special. You would not know it had planets or life. You would not know a civilization existed there. You would see just another star in a sky filled with thousands of stars. This is the reality of interstellar space. Every civilization, if there are others, lives in isolation. Communication across light years is slow. Messages take years to arrive. Even if two civilizations wanted to talk, the conversation would be delayed by enormous stretches of time. If they were 10 light-years apart, a simple hello and hello back would require 20 years. Imagine a friendship, or an alliance built on messages exchanged every 20 years, it becomes almost impossible. Stars are too far apart. Communication is too slow. Civilizations, if they exist, would develop independently, separated by time and distance. The Milky Way has hundreds of billions of stars. Many of them have planets. Some of those planets may have conditions suitable for life, but the emptiness between these systems is so immense that life could be common yet unreachable. The nearest star might be close in cosmic terms, but it is unimaginably far in human terms. That paradox, nearby yet unreachable, defines our entire place in the galaxy. What makes this even more astonishing is that the nearest stars are not exceptional. They are not special. They're simply the closest points of light in a galaxy filled with unimaginable numbers of stars. Most people never think about how far a star really is. They look up at the night sky and see hundreds of stars twinkling as if they were lamps hanging from a ceiling. But those stars are not close. The light you see from them has been travelling for years, decades, centuries, or even millennia. You are seeing ancient light from distant worlds that you will never visit. If you look at Sirius, the brightest star in our night sky, you're seeing it as it was about 8.5 years ago. If you look at Vega, you're seeing it as it was 25 years ago. If you look at Deneb, one of the brightest stars in the constellation Cygnus, you're seeing it as it was more than 1,000 years ago. And these stars are still relatively close compared to most stars in the Milky Way. Each star is a distant sun with its own history, its own planets, its own story written in light, and the closest ones are no exception. Alpha Centauri A and B, the two largest stars in the system, resemble our Sun in many ways. They shine brightly, orbiting each other in a slow, majestic dance. If you were to stand on a planet orbiting one of them, you might see two suns in your sky, a golden pair, each rising and setting, casting double shadows. And yet, even these stars, the ones most similar to our own, remain impossibly far. Standing on a planet around Alpha Centauri, you could look up and see the Sun as a bright star in the sky. It would not dominate the heavens. It would look like something familiar, yet distant, a reminder of how small our presence is in the galaxy. Earth would be invisible. Humanity would be nothing more than a whisper of light lost in the background glow. The more you think about this, the more the distances begin to overwhelm you. You begin to understand why interstellar travel is not simply a matter of building better engines. The distances are not large in the way oceans are large or continents are large. They are large in the way time is large. They stretch across centuries. They stretch across the lifespan of civilizations. They stretch across the rise and fall of entire cultures. And yet, despite this impossibility, there is something beautiful about the nearest stars. They remind us that we belong to a larger structure. We are part of a vast, spiral galaxy filled with hundreds of billions of stars. Our Sun is not alone. It is one point of light in an enormous island of stars. The nearby stars form our local neighbourhood, a tiny region of the Milky Way that we can map with precision. We can measure their distances. We can calculate their motions. We can discover their planets. Even if we cannot reach them, we can learn their stories. This is the power of the light year. It doesn't just measure distance, it connects us to other stars, to other systems, to the possibility of life beyond Earth. Every star we see is part of a cosmic family, spaced widely apart, but sharing the same galactic home. And though the distances isolate us, they also allow each star to exist without interference, forming its own worlds, its own history, its own potential for life. We stand in a universe that is too large for us to cross, but not too large for us to observe. Light brings us the past, 1 year at a time, from every star in the sky. And the nearest stars, though unreachable for now, remind us that even in this vast emptiness, we are not alone. The journey beyond our stellar neighbourhood will take us into deeper structures, the Milky Way itself, a galaxy that stretches so wide that even light needs more than 100,000 years to cross it. The distances will grow, the emptiness will deepen, the scale will expand beyond anything we've seen so far. And as we continue, the light year will remain our guide, our ruler, our connection to everything too far to touch. When you look up at the night sky, you might feel as if you're seeing the universe in the present moment, as though every star is shining for you right now. It feels like the sky is a giant map of what exists this very second. But the truth is very different. You never see the universe as it is. You only see it as it was. Every star is a memory. Every galaxy is a message from the past. Every piece of light reaching your eyes has been traveling for years, centuries, thousands of years, or millions of years before you see it. The night sky is not a picture of what exists today. It is a fossil record glowing in the darkness. This is one of the most profound consequences of the light year. Distance becomes time. The farther away something is, the older the light you receive. When you understand that, the sky transforms from a still image into a slow, unfolding movie of cosmic history. You become not just an observer of space, but an observer of time itself. Start with something close, the moon. When you look at it, you're seeing it 1.3 seconds ago. That tiny delay is too small to notice, but it's real. The sunlight bouncing off the moon hits your eyes more than a full second late. Nothing in your daily life has this kind of delay. When you speak to someone in the same room, the sound reaches them almost instantly. When you turn on a lamp, the light fills the space before you. Even realize it, but even at this small scale, the universe shows you that nothing is truly instantaneous. The sun sits 8 minutes away at light speed. That means the sunlight touching your skin left the sun 8 minutes earlier. You will never see the sun now. You can only see the sun's past, and this applies to everything in space. The farther something is, the deeper into its history you look. Look at Sirius, the brightest star in the night sky. The light you see tonight left Sirius 8.5 years ago. You are seeing the star as it was almost a decade ago. A decade of human life has passed during the journey of that light. People were born. People grew. People died. Whole chapters of your life happened while that single beam of starlight travelled through space. Look at Vega, a bright white star in the constellation Lyra. You're seeing it 25 years in the past. Whatever Vega is doing right now, whatever storms rage on its surface, whatever changes are unfolding, you won't know until a quarter century from now. The light reaching you tonight remembers a world before smartphones existed, before many people alive today were born. Look at Deneb, one of the brightest stars in the entire galaxy. Now you are looking back more than 1,000 years, over a millennium. The light hitting your eyes tonight began its journey before the modern world existed. It left Deneb when ancient civilizations were rising and falling on Earth. Long before electricity, long before telescopes, long before almost every structure humans have ever built. You are seeing light older than most of human history. And that's just the nearby stars. Now consider Betelgeuse, a giant red star in Orion. It sits hundreds of light years away. You see it as it was centuries ago. It could have exploded already. It could be gone at this very moment. But you won't know until the light reaches Earth. You're watching a star whose present state is hidden behind a curtain of time. If Betelgeuse had gone supernova 200 years ago, we would still be waiting for the explosion to appear in the sky. This delay created by distance is not a flaw. It is the structure of the universe. Light has a speed, space has a size, and time becomes part of everything we observe. When astronomers look farther, the effect increases dramatically. When they observe stars thousands of light years away, the light they see began travelling before humans existed. Imagine looking at a star and seeing light that left when Earth was filled with mammoths, saber-toothed cats, and early humans carving tools from stone. This is not science fiction. This is everyday astronomy. When telescopes point toward distant clusters of stars, they capture light that predates civilization. When they study nebulae, the birthplaces of stars, they are often looking at events that happened before your language existed, before your culture existed, before your ancestors even knew what the universe was. Move farther still. Look beyond our local region of stars and into other galaxies, and you step into deeper pasts. When you see the Andromeda galaxy, glowing faintly as a blur in the night sky, you're seeing it as it was 2.5 million years ago. The light left Andromeda at a time when humanity was not yet human. Our ancestors were early hominins walking upright in the African grasslands, unaware that their descendants would one day build telescopes to look back at that moment. A photograph of Andromeda is a photograph of ancient light, a message that left an entire galaxy long before modern humans evolved. Now look at galaxies even farther away. Some of the galaxies captured by the Hubble Space Telescope and the James Webb Space Telescope are shown as they were billions of years ago. Billions. That means the light began its journey across the cosmos before Earth had animals, before Earth had plants, before Earth had a solid atmosphere, before Earth even formed continents. That light was already travelling long before dinosaurs existed, long before mammals appeared, long before human ancestors took their first breath. These galaxies show the universe as it was when it was young, when stars were first forming, when galaxies were small and chaotic, when cosmic structures were just beginning to take shape. You are looking into the childhood of the cosmos. Every telescope is a time machine. The farther you look, the older the light becomes. The entire observable universe is a layered history book, with the nearest objects showing the most recent chapters and the farthest objects showing the earliest pages of creation. The speed of light forces the universe to reveal itself in time slices. There is no other way to see it. You cannot speed up the process. You cannot see a galaxy as it is right now if it is billions of light years away. You must wait billions of years for that light to arrive. This creates a strange kind of beauty. The night sky is not a single moment. It is a collection of moments spread across time. Every star is frozen in its own era. The nearest ones show you decades ago, the middle ones show you centuries ago, and the farthest ones show you deep cosmic history. Even the Milky Way itself has this layered structure. The light from stars on the far side of our galaxy takes thousands of years to reach us. We are seeing different regions of our own home galaxy at different points in time. Our galaxy is not a single picture. It is a mosaic of ages. The light year becomes not just a measurement of distance, but a translation tool. It tells you how far away an object is and how old the picture is. When astronomers say a galaxy is 100 million light years away, they are saying two things at once. The galaxy is 100 million light years distant, and the image you see is 100 million years old. The galaxy might look different today. Its stars may have evolved, its shape may have changed, new stars may have formed, old stars may have died, but we won't see any of that until the light from those events reaches us. This delay shapes everything we know about the universe. It is why we understand how galaxies evolve. It is why we can see the early universe by looking far away. It is why astronomy feels like archaeology, but instead of digging into the ground, we look into the sky. What makes this even more incredible is that the universe is expanding. As space stretches, light travelling across it is stretched too. It becomes redder, longer in wavelength, older in appearance. The farthest galaxies we see are not only distant in space, they are distant in time in a way that reveals the first moments after the Big Bang. We see them as tiny, primitive, chaotic clusters of stars. We see them before they grew into the massive, elegant spirals that fill the modern universe. We are watching the universe grow up. Light gives us the only record of this growth. There is no other messenger that carries the past across cosmic distances. Sound cannot travel in space. Physical objects move too slowly. Even gravitational waves, powerful and mysterious, travel at the same speed as light. Light is the universe's historian. It is the storyteller of everything that has happened. And this storytelling is not limited to galaxies. Even our own Milky Way is full of ancient messages. When you see the light from a supernova remnant, you're seeing the afterglow of a star that exploded long ago. When you see the light from a nebula, you're seeing the early stages of star birth. The universe is always changing, but the changes reach you slowly, filtered through the speed of light. This is why the night sky feels magical. It is filled with frozen moments. Some stars are living their prime, some are dying, some are already gone, but still shine through their old light. You could be looking at a star that collapsed into a black hole centuries ago, and you would have no idea until the last light reached you. The reality is simple but profound. The sky you see is not the universe today. It is the universe as it used to be. And the farther you look, the older the universe becomes. The light year turns the universe into a grand timeline. It turns every direction into a window into history. It turns the night sky into a museum of cosmic events. And now that we've seen how distance becomes time, the next step is even more overwhelming. The scale of the galaxy itself, a structure so vast that even light years begin to feel small. Once you understand how far the nearest stars are, the next leap is the one that truly bends the mind, the scale of the Milky Way itself. Everything up to this point, the planets, the solar system, the outer darkness, even the nearest stars, all of it fits into a tiny corner of our galaxy. In fact, if the Milky Way were a giant city, our entire solar system would be a single house on a quiet street. The nearest stars would be the neighbouring houses, and the city around you would stretch for thousands of kilometres in every direction. The Milky Way is enormous on a level that feels almost unreasonable. It is about 100,000 light years across. Think about that number slowly. 1 light year is already beyond imagination. Now take 100,000 of those and stack them next to each other. That is the size of our galaxy. Light, moving at the fastest speed the universe allows, needs 100,000 years to travel from one end of the Milky Way to the other. 100,000 years ago, humans were still living in caves, hunting with stone tools, sharing the planet with mammoths. 100,000 years is longer than the entire span of recorded human civilization, and that is just the width of our own galaxy. When you look up at the Milky Way band stretching across the night sky, glowing like a river of light, you're seeing a tiny portion of this enormous structure. You're looking into the dense centre of our galactic disk from inside it. You're seeing the combined glow of billions of stars that are packed tightly together in that direction. But even though the Milky Way looks crowded, we know the truth. The stars are still separated by light years of empty space. The crowded glow you see is an illusion created by distance. The stars look close because their light overlaps in your eye. In reality, each one is an island floating in its own vast ocean. The Sun sits in a region of the Milky Way called the Orion Arm, a small spiral arm tucked between two of the galaxy's major arms. It is not near the centre and not near the edge. It lives in a quiet, average neighbourhood. Nothing dramatic, nothing unusual. We're far from the violent, bright core where stars are packed tightly and black holes stir the environment. We're also far from the cold, empty outskirts where fewer stars form. In many ways, this quiet middle region is what made life on Earth possible. Too much radiation near the centre, and life struggles. Too few stars near the edges, and the materials needed for planets may not be available. The Sun sits in a calm, stable zone, a cosmic suburb with good conditions. But even in this calm region, the scale is staggering. The nearest spiral arm to us is thousands of light years away. The galactic centre is more than 25,000 light years away. That means the light we see from the centre tonight left thousands of years before the pyramids of Egypt were built. Long before writing existed, long before any modern culture began, we are seeing the Milky Way's heart as it was in ancient times. At the centre of the galaxy is a supermassive black hole called Sagittarius A Carinae. It contains the mass of over 4 million suns. You cannot see it directly because no light escapes it, but you can see the stars orbiting around it. They move in tight, fast loops, like planets orbiting an invisible sun. Some of these stars complete their orbits in just a few decades. This is how we know the black hole exists. Something huge and invisible is pulling them with incredible force. The strange part is this: even though Sagittarius A is unimaginably massive, it looks tiny from Earth because it is so far away. The distance softens the gravity we feel. The center of the galaxy is wild, crowded, violent, full of energy and radiation, but Earth floats safely on the edge of this cosmic storm, protected by distance. Distance protects us everywhere in the galaxy. Supernova explosions, when massive stars die in spectacular detonations, can destroy planets and sterilize regions of space. But space is so large that most stars are far enough apart that their death only affects their immediate surroundings. Gamma ray bursts, the most powerful explosions in the universe, can strip atmospheres from planets thousands of light years away. But again, the scale of the galaxy prevents most bursts from harming anything too far away. The galaxy's size is not just impressive, it is protective. Now imagine zooming out. You move upward, away from the plane of the galaxy, until its spiral shape becomes clear. At first, it looks like a flat disk, then the spiral arms appear. Long, sweeping arcs of stars, gas and dust winding around the center. Our entire solar system orbits around this structure. And how long does one orbit take? About 230 million years. The last time Earth was in this position in the galaxy, dinosaurs ruled the world. The first mammals were small and primitive. There were no humans, no continents arranged as they are today, no familiar life forms. That means everything you know, every story, every civilization, every invention, happened while the solar system was moving through a tiny fraction of one orbit around the galaxy. Humanity has been alive for less than 1% of the sun's current galactic journey. When you realize this, you begin to feel the weight of cosmic time. The galaxy does not evolve on human timescales. It evolves on geological timescales, on cosmic timescales, on spans so long that your entire species is only a brief moment. Galaxies are not static. They collide, merge, twist, and reshape themselves over billions of years. The Milky Way is no exception. It has swallowed smaller galaxies in the past, and it will collide with the Andromeda Galaxy in about 4 billion years. When that happens, the night sky will transform dramatically. Andromeda will grow larger and larger, turning from a faint smudge into a brilliant swirl. Eventually, the two galaxies will merge into a single, enormous structure. It won't be a violent collision like two solid objects crashing. Instead, it will be a slow, graceful intermingling. Stars will mostly pass by one another because the space between them is so vast, but their combined gravity will warp the shapes of both galaxies. Even now, Andromeda is more than 2.5 million light-years away, and the light you see from it tonight began its journey when early humans were not even humans yet. That smudge of light in the sky is a portal into the deep past, and that portal is drifting closer every day, pulled toward us by gravity. The galaxies are on a collision course, their dance guided by the laws of physics that govern everything from planets to stars to entire star systems. Now zoom back in. Look at the Milky Way again from afar. It is a flat disk, glowing softly, sprinkled with hundreds of billions of stars. And inside that disk is everything you've ever known. Every planet, every comet, every nebula, every civilization that might exist on worlds we haven't discovered. Everything is contained within this island of stars, a vast cosmic city in a universe filled with similar cities. But here's the part that makes the mind break a little. The Milky Way is just one galaxy, one among trillions. The universe is filled with galaxies of all sizes, spirals, ellipticals, irregulars, and they are separated by distances measured in millions of light years. You could fit entire galaxies between galaxies. The empty space between them is so large that even light takes millions of years to cross it. This is where the scale jumps again. You thought light years were huge when measuring star distances, but when you start measuring galaxies, you use millions of light years as casually as you use thousands to measure stars. The Milky Way is one giant island. Andromeda is another giant island. Dozens of smaller galaxies orbit both of them. Together, they form a group called the Local Group, a gravitational family of galaxies held together across millions of light years. Even within the Milky Way, our place is small. The solar system is a grain of dust floating inside a grand spiral. Our entire history fits into a tiny sliver of one orbit, and everything we've ever done, created or imagined, is contained within a radius that light can cross in a few hours. Yet we are part of something enormous, something ancient, something beautiful, something so vast that even light, racing non-stop, needs 100,000 years to paint a full picture of our galaxy. The Milky Way reveals a truth that is both humbling and inspiring. You are part of a structure too large for your mind to hold. And despite the unimaginable distances, you are connected to every corner of it by light, the silent traveller carrying stories across time. We have now arrived at the scale where galaxies themselves become our units of measurement. The next part will take the final leap, from galaxies to the universe itself, distances measured not just in millions, but in billions of light years. When you finally understand the scale of a galaxy, you might think you've reached the limit of how far the mind can stretch. After all, what could be bigger than 100,000 light years? What could be more overwhelming than the idea that light takes longer to cross the Milky Way than the entire history of human civilization? But the universe is not satisfied with simply being large. It goes far beyond galaxies, far beyond anything we normally picture when we think of space. If the Milky Way is an island, then the universe is an ocean so vast that even calling it enormous feels inadequate. Around the Milky Way lies the Local Group, a small cluster of galaxies held together by gravity. It includes Andromeda, the Milky Way's future collision partner, and dozens of smaller galaxies. The entire Local Group stretches about 10 million light years across. 10 million. That means light must travel for 10 million years to cross from one end to the other. The numbers have already grown so large that they barely feel like numbers anymore. They feel like abstract ideas, like something meant for textbooks or simulations, not for the human mind. And yet the Local Group is tiny compared to what surrounds it. It is one small cluster in a vast cosmic web. Our Local Group, along with thousands of other groups and clusters, forms a larger structure known as the Virgo supercluster. This supercluster stretches over 100 million light years in diameter. 100 million light years. When you say those words, it's difficult to attach any meaning to them. Even a million felt huge when we started. Now we're dealing with 100 million, a space so enormous that entire galaxies, each containing hundreds of billions of stars, float like specks inside it. But the universe keeps growing in scale. The Virgo supercluster is not the final layer. It is part of an even grander structure called Laniakea, our home supercluster, the continent of galaxies that contains us. Laniakea spans over 500 million light years, 500 million light years. Imagine the light that leaves one side of this supercluster. It will continue travelling for 500 million years before reaching the other side. By the time that Photon finishes its journey, continents on Earth will have drifted, species will have evolved or vanished, oceans will have shifted, and humanity will be unrecognizable or extinct. That Photon's trip is longer than the existence of complex life on Earth. Even this is not the end. Laniakea is one of many superclusters woven into the cosmic web. a vast network of filaments stretching across billions of light years. Each filament contains galaxies and gas and dark matter, forming structures so large that they defy the imagination. Between these filaments lie enormous voids, vast empty spaces where almost nothing exists. Some of these voids are hundreds of millions of light years across, containing only a few lonely galaxies inside their darkness. These are deserts of the cosmos, the silent regions untouched by star formation or galactic collisions. This large-scale structure is the skeleton of the universe, shaped by gravity and the expansion of space itself. And speaking of expansion, this is where everything becomes even stranger. The universe is not static, it is expanding. Galaxies are moving away from each other, carried by the stretching of space. The farther a galaxy is from us, the faster it recedes. And beyond a certain distance, galaxies are moving away faster than light, not because they're breaking the speed limit, but because space itself is expanding between us and them. This means that the light they emit today may never reach us. This leads to a concept even more mind-bending than light years: the observable universe. The observable universe is the region of space from which light has had time to reach us since the beginning of the universe. The universe is about 13.8 billion years old, but because space has been expanding during that time, the observable universe extends to a radius of about 46 billion light years in every direction. The diameter, then, is about 93 billion light years. Think about that. 93 billion light years. You are living inside a sphere so large that even light, travelling since the birth of the universe, has not had time to cross it. The observable universe contains trillions of galaxies, not billions, trillions. Each one is a massive, complex system of stars, planets, dust, and dark matter. Each one contains its own history, its own story, its own possibilities for life, for worlds, for civilizations that may have risen and fallen long before Earth formed. And the observable universe is not the entire universe, it is only the portion we can see. Beyond that boundary lies the unobservable region, space whose light has not yet reached us and may never reach us. The true universe might be hundreds of billions of light years across. It might be infinite. We don't know. We may never know. The light year unravels the universe for us, but it also reveals the limits of what we can understand. Imagine floating somewhere in deep space, surrounded by darkness. A photon reaches you, carrying the faint glow of a galaxy billions of light years away. That photon began its journey before Earth even existed. It passed by the birth of our sun, the formation of the planets, the rise of life, the evolution of humans. And only now, after billions of years in flight, does it encounter your telescope or your eye. That single particle of light has witnessed a history longer than all of human evolution, longer than the lifespan of most stars. When telescopes like the James Webb collect light, they are not taking ordinary pictures. They are harvesting ancient messages. They are listening to the universe's earliest whispers. They are studying galaxies as they were when the cosmos was young, chaotic, and filled with newborn stars. They are watching the earliest structures form from clouds of hydrogen and helium. They are observing the first chapters of existence. The universe you see through a telescope is not the universe now, it is the universe then. Every direction you look, you are looking into the past. The nearby stars show you recent history. The distant galaxies show you ancient history. And the faintest, most distant light shows you the universe only a few 100 million years after the Big Bang. Beyond that, the light becomes too stretched, too faint, too old for us to detect. But that doesn't mean nothing exists there. It simply means the universe's earliest moments lie beyond our observational reach. This creates a profound realization. The universe has a horizon, not a physical edge, but a limit to what we can see. The expansion of space is pulling distant galaxies away from us so rapidly that some will soon slip beyond our horizon forever. Their light will never reach us again. They will vanish from our view, not because they cease to exist, but because the universe grows so quickly that the distance between us becomes uncrossable for light. Imagine standing on a shore, watching ships drift away. You watch them shrink on the horizon until they disappear. But unlike ships on Earth which can come back, these cosmic ships never return. They fade into a darkness that light cannot overcome. The universe is filled with galaxies we will never observe, never study, never even know about. They exist in a realm permanently separated from us by the speed of light and the expansion of space. This is the final consequence of light years. They define not only how far we can see, but how much we can know. They reveal the scale of the cosmos, but also the limits of our reach. They show us an enormous universe, but also a universe filled with barriers we cannot cross. And yet, despite all these barriers, here we are, a species living on a small planet, orbiting a small star in a quiet arm of a spiral galaxy, able to measure the distances to galaxies billions of light years away, able to calculate the age of the universe, able to observe cosmic events from the dawn of time, able to understand the rules that bind the cosmos together. Light years are the bridge that connects our tiny world to the vast universe beyond it. They are the numbers that allow us to translate unimaginable distances into something we can study. They are the way we measure time, distance, age, and structure. And now, at the end of our journey, the most astonishing truth remains. The universe is not just bigger than you think. It is bigger than you can think, bigger than your imagination, bigger than your intuition, bigger than the language we use to describe it. Light years stretch the mind until it breaks, then force it to rebuild itself on a cosmic scale. You now understand why light years exist, why the universe uses time as a measure of distance, why the night sky is a map of the past, why even the closest stars are incredibly far away, why galaxies lie in vast islands separated by emptiness, why the observable universe has a horizon, and why the true universe may stretch far beyond anything light can ever reach. In the end, the light year is not just a measurement, it is the story of the universe written in distance and time. It is the language of the cosmos, and it is the limit and the key to everything we know.